Hi everyone, we're continuing with our journey through right triangle trigonometry. Now you might be wondering how we get the basic trig values for things like 30 degrees, 45 degrees, and 60 degrees. For example, how would we find the sine of 45 degrees? Well, it turns out that we're going to use two families of similar triangles. These are special triangles. One family is the 45, 45, 90-degree family of similar triangles. Again, similar triangles have the same shape, but maybe different sizes. Now these 45, 45, 90-degree triangles are sometimes known as isosceles right triangles. Take a look here. We have here a 45, 45, 90-degree right triangle. These are by definition isosceles, meaning that the two legs have the same length. They're congruent. Of course, the hypotenuse is still the longest side. Now, it makes sense that in a triangle, equal or congruent angles will face equal or congruent sides. Now, the most basic 45, 45, 90-degree triangle, the basic triangle we like to base everything on, is this one over here, where each leg length is 1 unit, say 1 meter. By the Pythagorean theorem, we then get that the length of the hypotenuse is the square root of 2. By the way, the fact that the square root of 2 is an irrational number here, this hypotenuse is irrational, that really freaked out the ancient Pythagoreans. In fact that this was an irrational number so freaked them out that there are legends that Pythagoras would have people who released this secret taken out, literally taken out. They'd be thrown off of boats with an anchor. Or there was a rumor that Pythagoras himself stabbed someone who revealed the secret, that the square root of 2, this hypotenuse, was irrational. So I hope that you students appreciate this knowledge that you're getting, because people have died for it. Okay, anyway, so here we have 1 meter, 1 meter. This is the square root of 2 meters, irrational. All right, now, given these side lengths, hey, we can come up with the sine of 45 degrees and so forth. So what is the sine of 45 degrees? Well, SOHCAHTOA, sine is opposite over hypotenuse. It's 1 over root 2. Pulling this up over here. The sine of 45 degrees, also the cosine of 45 degrees. Cosine is adjacent over hypotenuse. That's also 1 over root 2. We rationalize the denominator and we get root 2 over 2. So both sine of 45 degrees and cosine of 45 degrees, again, it's good to put parentheses, they both have as their value root 2 over 2. Now from these, we can also get the reciprocal values, the cosecant of 45 degrees and the secant of 45 degrees. Now it's true that if you turn this guy upside down, 2 divided by the square root of 2 is in fact root 2. If you don't believe me, multiply by root 2 on both sides, and we see that 2 equals root 2 times root 2. That's a true statement. So we could do it that way. We could turn this upside down. 2 over root 2 is root 2, but wait a minute. Look at this guy. One advantage to the unrationalized version of these trig values is that if you take this guy and turn him upside down, hey, you get root 2 over 1. So these unrationalized versions of these trig values can be useful, especially when you're taking reciprocals. The reciprocal of this is clearly root 2. So this is the cosecant and the secant of 45 degrees. Now what about the tangent of 45 degrees? SOHCAHTOA, TOA, tangent of 45 degrees is opposite over adjacent. 1 over 1 is 1. And its reciprocal, cotangent of 45 degrees, is also 1. So fairly quickly, we're able to get all 6 basic trig values for 45 degrees by using the properties of the 45, 45, 90-degree triangle you see here. Again, it's a whole family of similar triangles, but this is the nicest, easiest one to work with. 1, 1, root 2. Okay, Now, bear in mind for similar triangles, if this is 10 meters, for example, if that's 10 meters, then that's 10 root 2 meters. So you have similar, in fact, you have the same trig values, even if you blow up or shrink this triangle. Because remember, these trig values correspond to ratios of sides on this right triangle. So even if we multiply everything by 10 meters, the ratios between pairs of sides will still be the same. For example, the sine of 45 degrees will always be 1 over root 2, or root 2 over 2, even if this is 10 meters and this is 10 root 2 meters. All right. So what about 30 degrees and 60 degrees? Well, we're going to look at this second family of similar right triangles, a second family of important, special, similar right triangles, 30, 60, 90 degree triangles. Now, it turns out that in order to analyze these, it's easy to begin with an equilateral triangle, a triangle in which all three sides are congruent, they have equal lengths, and all three interior angles are 60 degrees. So we're going to start with this equilateral triangle over here. Let's say this is 2 meters, 2 meters, 2 meters. So this big triangle here is an equilateral triangle with common side length 2 meters. 2 meters turns out to be convenient because we're going to split this side in half so that this is just 1 meter. Okay, so we start with this equilateral triangle of side length 2 meters, and we're going to drop this perpendicular, which is a common trick in right triangle trig. We drop a perpendicular, we have a right angle over here, and the 60-degree angle over here is bisected into 30 degrees and 30 degrees. Now, what we have now is a situation where we have two congruent right triangles. Let's look at the one in red here. We have here a 30, 60, 90 degree right triangle. 30 degrees here, 60 degrees here. Because there's a different angle measure, I'll use 2 arcs, and the right angle, 90 degrees over here. Okay, now remember, we bisected this side over here. We split it into 2 equal sized pieces. If the entire side length here is 2 meters from here to here, then it's just 1 meter from here to here. 1 meter over here. This side length is still 2 meters. The hypotenuse is still 2 meters. That was the original side length. So then, how do we get this root 3 meters? Well, it's from Mr. Pythagoras, the Pythagorean theorem. From the Pythagorean theorem, we get that the missing side length here is root 3 meters. Again, it's irrational, like the root 2 meters from before. So this is our favorite 30, 60, 90 degree right triangle, the one with side lengths 1, root 3, and 2, using the same unit. The hypotenuse of a 30, 60, 90 degree right triangle will always be twice as long as the shortest side, and the medium side will always be root 3 times as long as the shortest side. In a 30, 60, 90 degree right triangle, the shortest side faces the smallest angle, the 30 degree angle. The medium side length faces the medium angle, the 60 degree angle. And of course, the hypotenuse, the longest side, faces the largest angle, the 90 degree angle. In general, in a triangle, the shorter sides face the smaller angles, the longer sides face the larger angles. Now, from these side lengths, we can get ratios and get the sine of 30 degrees and so forth. So what is the sine of 30 degrees? What is the sine of 30 degrees? I'll use blue to make things clearer. What is the sine of 30 degrees? All right, the sine of 30 degrees, SOHCAHTOA, sine of 30 degrees will be opposite over hypotenuse. The opposite side length, 1 unit. The hypotenuse, 2 units. The sine of 30 degrees is 1 over 2. It's 1/2. The sine of 30 degrees is 1/2. Also, the cosine of 60 degrees. Let's shift our perspective. If we look at the 60-degree angle, the cosine of 60 degrees is given by adjacent over hypotenuse. The adjacent side has length 1 unit. The hypotenuse has length 2 units. Adjacent over hypotenuse is again 1/2. So both the sine of 30 degrees and the cosine of 60 degrees will be 1/2. And the fact that these two values are equal is no coincidence. That's going to take us to the cofunction identities. All right. Before I go on to that, I'll very quickly observe the sine of 60 degrees will be √3/2. That's also the cosine of 30 degrees. But notice that we have that pattern, right? It seems like the sine of one angle here is the cosine of the other acute angle over here. The sine of 30 degrees equals the cosine of 60 degrees. Likewise, the sine of 60 degrees equals the cosine of 30 degrees. Now, why is that? Remember, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Let's take a look at this shortest side here with length 1 unit. It's the opposite side for 30 degrees and the adjacent side for 60 degrees. Whereas the √3 here is the length of the opposite side for 60 degrees, yet it's the adjacent side for 30 degrees. So when we switch from one acute angle to the other angle, we're switching the adjacent and opposite sides. So it makes sense that the sine of 30 degrees is the cosine of 60 degrees, because the opposite for this angle is the adjacent for this angle. Oh, and how are these two angles related? 30 degrees and 60 degrees add up to what? They add up to 90 degrees. So that makes these two angles what? Complementary. Complementary. We are now going to talk about the cofunction identities, which represent the third group of basic trig identities. Remember, we had the reciprocal identities, the quotient identities. Now we have the cofunction identities. Cofunctions are short for complementary trig functions. By the way, I should technically write these out fully, but here I'm using their abbreviations. In case you're wondering how these were related, these are pairs of cofunctions, sine and cosine. They represent a pair of cofunctions. Tangent and cotangent, a pair of cofunctions. Secant and cosecant, a pair of cofunctions. So in case you're wondering, well, how are these related? Sine and cosine, tangent and cotangent, secant and cosecant. Well, I'll give you an example. The secant of 30 degrees will be the cosecant of 60 degrees. And the secant of 60 degrees will be the cosecant of 30 degrees. Again, that's because we're switching the adjacent and opposite sides when we switch angles. Cofunctions of complementary angles are equal. Now, you can write out a whole bunch of cofunction identities, but it's easiest to remember this principle. Cofunctions of complementary angles are equal. So, for example, the sine of 30 degrees is equal to the cosine of 60 degrees. These were both equal to 1/2. 30 degrees and 60 degrees are complementary angles. Sine and cosine are cofunctions. Cofunctions of complementary angles are equal. The sine of 30 degrees equals the cosine of 60 degrees. Again, that reflects the fact that when we switch from one angle to its complement, we're switching the adjacent and opposite sides. All right. So how can we write out the cofunction identities? And bear in mind that these go beyond acute angles and even right triangles. So this will apply even if theta is 1,000,000 radians or -6 radians. This applies where theta is any real value. You could think any angle in degrees or any angle in radian measure, any real number, really. The cofunction identities. How can we write out some of these? There are a whole bunch of them. If theta is measured in radians, then for all real values of theta, these will be true. These two statements will be true. The sine of theta will equal the cosine of its complement. I claim that pi over 2 minus theta is the complement of theta. If we extend the idea of complementary angles to any pair of angles whose measures add up to 90 degrees or pi over 2 radians. So theta doesn't have to be acute. Theta could be negative or like 1,000,000 radians. I'm going to extend the definition of complementary angles beyond Math 104. So we can say, for example, negative 10 degrees and 100 degrees are complementary. Okay, so theta can be any real number, any angle as a real number in radian measure. I claim this is the complement. And why is that? Well, if we add these two together, if we take pi over 2 minus theta and add back the theta, what happens? We just get pi over 2. Pi over 2 minus theta plus theta, that takes us back to pi over 2. So again, I'm claiming that theta and pi over 2 minus theta are complementary in the sense that they add up to pi over 2. Likewise, cosine of theta will always equal the sine of the complement, pi over 2 minus theta. The same is true for secant and cosecant, cosecant and secant, tangent and cotangent, cotangent and tangent. If you have a pair of cofunctions and a pair of complementary angles, cofunctions of complementary angles are equal, or they're both undefined. For example, the tangent of 90 degrees is undefined, so is the cotangent of 0 degrees. Speaking of degrees, if theta is measured in degrees, then basically we replace pi over 2 radians with 90 degrees. The sine of theta in degrees is equal to the cosine of 90 degrees minus theta. Because theta and 90 degrees minus theta are complementary. They add up to 90 degrees. Likewise, the cosine of theta equals the sine of the complement, 90 degrees minus theta. Again, we can say the same for secant and cosecant, cosecant and secant, tangent and cotangent, cotangent and tangent. Cofunctions of complementary angles are equal. Now you can see how it's easier to remember the cofunction identities by remembering this statement. Cofunctions of complementary angles are equal because there are many, many cofunction identities. Many things you could write out. All right. So that's our tour of right triangle trigonometry. In our next part, we're going to analyze the unit circle approach, which will be consistent with the right triangle approach, but it's much nicer for quadrantal angles and maybe for angles in other quadrants besides quadrant 1. And that's next time.